Right, now let's consider something a little different. So suppose we have we're still going to be looking at a force on a current, but now we will look at a curved wire, not a straight wire, not a straight one. And things will change a little here. Same principle, same ideas, but we'll have to change things a bit. So suppose we have a magnetic field. And let's draw this picture big enough. Here's a magnetic field. And let's add more. So here's the magnetic field, and then let's say we have a wire here that does something like this. Here's a current. The current runs into this field, gets to this point, and then it curves around. I'm going to try to draw this big enough because this is the part that is going to be tricky. Let's say this is a semicircle. Let's give it a better shot. So it runs like this, and then let's say that it actually comes just to the edge of the magnetic field, and then it runs out. So the current flows in, goes into the field, goes around, and then eventually it comes out. And then the question is, what is the force exerted on this whole wire? So perhaps you loop this out and there's some kind of a battery here on the bottom, and then it just connects like this. But the magnetic field is only there where I drew it. So the magnetic field is confined to this little rectangle. Right, so this is where you have the magnetic field. Magnetic field does not extend beyond this little space. So not all of the wire in the circuit is exposed to the magnetic field, and therefore not all of the current is going to have a force acting on it. Only some sections. So what we will have here is the question is, what is the net force? So let me state this thing. What is the net force on the wire? And so it would make sense to divide this into some sections. This little section of the wire here, that's easy to do. It's easy to figure out the force on this little section of the wire. The curved section of the wire, that's going to be trickier, so we'll do that part as well. And then let's just ignore this little piece here in the corner. I meant to draw it in a way that the curve comes out to the edge. So first thing we should notice is that F net would be the sum of F1 plus F2. By F1, I mean the force acting on this wire, and that would be in this direction. By F2, I mean the force acting on this wire, and this would be, well, let's draw a few. Here, 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 here. And in fact, what you're going to get is there's a force acting on this. So we can calculate F1. F1 is easy to do. You would use the right-hand rule to figure out the direction of this force, and that should be easy to do. So I'm going to leave that up to you to confirm that the force does in fact point up in this section of the wire. Now F1 would just be I times L times B times the sine of 90. 90 because you have 90 degrees between I and B. So you put 90 here, right? Magnetic field points into the page, current flows to the right. There's 90 degrees between them. The magnetic field itself, let's put some numbers on this thing. So let's say that the magnetic field is 2 Tesla, so it's a fairly strong magnetic field. Let's say that the length here, say that this length here is, let's just make something up. Let's say this is 0.2 of a meter. And then the current I, let's give it a value. So current I, let's say this is also 2 amps. We have 2 Teslas, 2 amps, and then 0.2 meters. So let's calculate F1. 2 times 0.2 times 2, we get, what do we get? We get 4 times 2, 8. For 10, so this is 0.8 newtons is what we get. And if I wanted to state this in a vector form, I would write that this is 0.8 newtons in the j hat direction, which I could also state like 0, 0.8, 0, then I would have newtons here. All right, so we have that. The coordinate system we're going to use is just going to be this: x, y, and then z comes out like this. So what I have to do is I have to figure out F2, where F2 is the force on this curved segment of the wire. Now F1 is the force on this entire segment here. Even though I drew one vector here, I represent by this one vector the force on the entire section of the wire. Here I drew a bunch of little vectors, and each force vector here represents a little bit of the force. Here's the F, here's the F, here's the F. Each vector that I drew represents a little bit of the force acting on that specific section of the wire, this specific section of the wire, this specific section of the wire, this specific section of the wire. And so F2 change the colors. F2 is going to be the sum of all of these little df's. So I have to look into that. Let's see if we can steal a little bit from the geometry here. There's a symmetry. That is, this is half a circle, and so there's some symmetry that we can, and that is always, whenever you have symmetry, you can things tend to work out a little easier. So consider this df here. It's going to have the x component, so some dfx. It is going to have also the y component, so some dfy. And then there's the angle theta. So here you have theta, and that angle theta is the same as this angle theta here. So there's theta there on the inside. Now we'll go to the other side, directly to the other side, and you will find another df here. And then this df was going to have dfx, dx component, is also going to have dfy, y component, and here's angle theta, which is going to be the same as the one on the other side. So this is same angle theta. Let's have theta here. So by symmetry, you should see that for every little section of the wire that you have on this side, you can find another section of the wire on the other side where the x components cancel out, because they will have the same magnitude, but they will point in opposite directions. The equation we will use is if F is I L cross E, then dF is I L cross E, the equation we're using. And so from this equation, it's easy to see that if I have the same current that flows through this little section, and as I have flowing through this little section, and this dl here has the same length as this dl here, and the magnetic field has the same value here as it does on this side, then the magnitude of this df will be the same as the magnitude of this df. Now, given that the angles here and here are the same, then this dfx will be equal in magnitude to this dfx, but they will point in opposite directions, so they'll cancel out. And you can see this, that this will happen for every single component, for every single section of the wire. So if you consider this here, this little section of the wire, the x component of the force on this section of the wire will be cancelled out by the f component of the force on this section of the wire, and the f component on this section of the wire will be cancelled out by the F component on this section of the wire. And maybe I should I draw? Well, I think that'll do. So all of the little DFs in the X direction will cancel out. Right, so let's use that symmetry. So what I can do is I can write that F2 is, we already know that that all of these little forces F's will point in the XY plane. So what I can write here is that this is just going to be F some X component, so F2X comma F2Y, and the Z component is going to be 0. From right-hand rule, I can see that this is the case everywhere along this wire. But F2X as a whole will cancel itself out. Let me write it like this. So F2 equals, that's not what I wanted, sum of all of the little DFs, but X components, and then Fy is going to be the sum of all of the little DFs, but the Y components, and then this is just 0. However, we just said that by symmetry, all of this will go to 0. So what I can write is that F2 is just going to be 0, comma, all of the Y components added together, comma, 0. That's good, so I made some progress. So I only have to focus on that. So let's figure out that piece, Fy, which is the integral of the Fy, going to be the same thing as df times, so let's maybe draw, well, that's okay, let me do that, we'll come back to that in a second. Let's draw something here. Let's take a random df, so let's take this one, but I want to redraw it so it's a little clearer. All right, so let's take a small section here of the wire. So here's a small section of the wire. This is a little bit of DL that I have. There it is. And then on this little DL, there's going to be a force that acts. I'm going to draw it bigger on purpose, so I have more room here. Here's DF. And then this DF is going to have the X component, dfx, and we know that this dfx here will be cancelled out by dfx on the other side, so we don't worry about it. But what we do need is we need this dfy. Now dfy is simply df, vector notation. dfy is simply df times the cosine of this angle. And that angle here is just theta. By theta, I mean this. So this theta is the same as this theta here. And so down here, I'm going to write df times the sine the angle theta. Probably should have used alpha, come to think about it, but anyways, we have what we have. And then note that this angle theta will vary. This angle theta will vary from, it's going to start at 0 and it will go all the way to pi. Reason being is that the smallest that this theta can be, so this is the theta I'm looking at. The smallest that this theta can be is here from this section, and so that'd be 0 all the way to the angle pi when you get to the other spot here, the other point. So I have this expression, so let's now write that Fy equals, for df, I'm going to, this is where I will take, going to be here, df equals I dl times b times the sine of the angle, call this alpha, where this angle is, this is the angle between b and dl. So I'm going to write, I'm down here, I'm going to write now I dl times b times sine of alpha times the sine of theta. And let me indicate that this df here, that's all of this. Now, theta, I already said what that was. So theta is just this. Alpha is the angle between DL and B. And so alpha, that's the angle between DL and B. And from the picture, it should be easy to see that DL is always perpendicular to the magnetic field. DL is always perpendicular to the magnetic field. And here DL is always perpendicular to the magnetic field. In other words, alpha is just 90 degrees because DL is perpendicular to the magnetic field. So I can now take another step and I can write that Fy equals I is a constant. That's just a constant current. In this specific problem, it's a constant current. B is also a constant, so I can pull this out. This is I times B. What I'm left with is DL times sine of 90 times the sine of theta. I'll take one more step here before I move the screen. So this will be I times B, and I have here sine theta dl. And remember, theta is the angle between 0 and pi. This comes out of the geometry of the problem. So let's move the screen. See if we can finish this up. dl is just the arc length. Now, you look at the picture there, dl is the arc length. So what I can say, I'm going to do it here on the side, but maybe in a different color. So let's do it in light green. So dl, that's just the arc length. We use s for the arc length, so I'm going to put s here. And this, by definition, something you should know is just theta. Sorry, this is r times the theta, where r is the radius of the circle you're looking at. So this is r. Right, so that's r. Now let's take this and plug it into our equation. So we're going to take this expression here. What we get therefore is Fy equals I times B, and then we have sine theta, and for the L I'm going to put times R times the theta. Now little r is a constant, so I can pull this out, and so I have Fy equals I B R sine theta. And this goes from 0 to pi. So when I do this, what I'm going to get is I B R cosine of the angle theta with a negative sign. So let's put negative here. And this is from 0 to pi. When I do that, I'm going to get cosine of, well, let's go ahead. So Fy equals I B R, and then remember cosine looks like this. So here I have 2 pi, this is pi, and so from this picture it's easy to see that what I end up with is minus cosine at pi, that's minus 1 minus minus, so this just gives me 1, and then minus minus plus 1, I end up with 2 I B R. So now what I can do is, this is Fy. Let's maybe take this color again. I'm over here, I'm looking at Fy here. Remember that, perhaps I should now write that the F net on this whole wire was F1 plus F2. And we figured out F1. In fact, F1 is right here, that's F1. That F1 was 0.8 j hat, and then F2 plus F2, well, this is my F2, it's just there's only y component to it, so this would be 2I B times R times, there's only y component, therefore this would also be j hat, and so the whole thing becomes 0.8 plus 2I dr j hat. Let's maybe calculate this, see what we get out of that. So this is 2 times the current, and the current was 2, magnetic field was 2, and the radius, I don't know if I ever said anything about the radius, so let's see what we said there. We didn't. Let's just give some number to this r. Let's say that r is 10 centimeters. This is 0.1 of a meter. And in that case, I would have 2 times 2 times 2 times 0.1, and so we get 4.8. Well, apparently it's 0.8 newtons. And so I would simply end up with 0.8 times 1.6 newtons in a j-hat direction. So this would be the total force on this whole thing. Let's maybe zoom out. All right, and that does it for a curved wire. Maybe keep in mind that what we did here is we took this equation for the force on a wire and force on a wire with a current in a magnetic field, L cross B. This works for a straight wire, but if you curve the wire, then you have to do it a little differently. You have to take it and break it up into little segments. You'd have I dl cross B is what you would use, and specifically then F becomes the sum of all of these little sections, all of these little forces. This is if the wire is curved. Put here curved wire. All right, and then there are some problems in the book. I think there's one sample in the book that you should look that is similar to this, and then there are a couple other problems in the back of the chapter that you should also look at.